Hey guys, so today we're going to be doing curve sketching again, this time with a polynomial. So we're going to apply, I remember I did one earlier this year with rational functions. Still the same concepts, but we're going to apply it to polynomials now. Yeah. So the first thing, intercepts. For the x-intercepts, you would have to solve a cubic equation. If the x-intercepts are too hard to find, usually in a polynomial they are, unless you're doing a quadratic function, you can just disregard. So don't even acknowledge it. You could use Newton's method to try to find some of the x-intercepts, but I doubt you would have that much time on a final exam or test. So yeah, you can just ignore it. The y-intercept is just where x equals 0, and that would just be 2, because 0, 0, 0 plus 2 gives you 2. Yeah. B, domain and range. The domain and range is like for it's the entire, like, it goes from negative infinity to infinity for both x and y. So there's not much to say there. For part C, it's not applicable. So like there's no asymptotes. None whatsoever. Like a polynomial function is continuous throughout its entire domain. But I will just indicate that as the function goes to negative infinity, it will go, as x goes to negative infinity, the function will go to negative infinity. And as the function goes to, as the x goes to infinity, the function will go to infinity. Let me try to think. Did I miss anything? No, there's no vertical, nothing. Okay, yeah. So D, critical points. Let's first find the derivative of this. So f prime x x cubed, the derivative of that is 3x squared. The derivative of negative 6x squared is 12x. And the derivative of 9x is 9. Just using the power rule here. So, okay, so we need to find out where this is equal to 0, first of all, to find some critical points. Let's see, so this would just be 3, and then it would be x squared minus 4x plus 3 when you factor it out. But that also is x minus 1, x minus 3 equals 0. So there's critical points at x equals 1 and x equals 3. Now, just because these are critical points doesn't mean they are for sure maxima or minima. You have to do some test. You can either do the first derivative test or the second derivative test. I know I still have to find areas of increase and decrease, but I'm gonna skip this step for now. I'll come back to it. I'm gonna do part E and then I'll come back to this part, okay? So to find concavity, we'll look at the second derivative, f prime prime x is equal to 6x. This 3x squared goes to 6x, negative 12x goes to minus 12, and the derivative of 9 is 0, and it equals 0 here. And there's only one candidate inflection point. This minus equals 0, so x equals 2. And this is obviously going to be an inflection point because when x is below 2, this is going to be negative, and when x is above 2, this value is going to be positive. So what we can say is f is, it's negative when it's below 2, so you can say it's concave down. I'm going to write CD for concave down at x less than 2. And concave up, CU for that. Okay, now back to this. So let's do the second derivative test. Let me just write that here. Second deriv, short for derivative test. Okay, so f prime prime 1, 6 times 1 minus 12 gives you negative 6. So x equals 1 is a local maximum. It's according to the second derivative test. F prime prime 3 will give you 6. It's a positive value. It's greater than 0. Since this is greater than 0, at 3, it's a local minimum. Now back to this, areas of increase and decrease. Well, the graph of 3x squared minus 12x plus 9, or x squared minus 4x plus 3, it looks something like this. At 1 and at 3, just graphing a parabola here. You can pretty much see that, like, from negative infinity to 1, it's f prime x is above 0, and it's above 0 at x greater than 3, and it's below 0 between 1 and 3. So based on this, you can say f is increasing at negative infinity to 1, union 3 to infinity, because these are where it's above 0, and decreasing at 1 to 3. Okay, so that is good. Now we have everything what we need to do for F. I'm gonna do F on an, I'm gonna share the screen with what the function looks like. So here, and I'm gonna share a different screen now. And as you can see, a lot of the characteristics this graph has, pretty much all of it, we've described in our sketch the curve things that we've been doing for the past 15 minutes. Like it's concave down from -infinity to 1, -infinity to 2. It looks like the cup is gonna leak out water. Like it has a shape of a hat, and from 2 to infinity, it has a concave up shape. It's increasing from -infinity to 1, and at 3 to infinity, and it's decreasing from 1 to 3. All of the details, yeah, even the y-intercept being at 2, it's all labeled here. To do part F, just like in the last case, you would probably try to find the values, find a few y values by inputting functions of x. Like maybe you would want to know exactly where the critical points are, so you would input f of 1 here, and then you would find f of 1 equals 6 and f of 3 equals 2 by inserting the values into this function here. You would find out f of 2 is 4. And then maybe you would find that f of 4 is 6, or f of -1 is something else if you wanted to. So yeah, that's pretty much how you do the graph for this. So great. I hope you liked this video. I'd love to stay, but for now, I gotta jump. I'll see you guys on the other side of the bridge. Catch you next time.